Hello, everyone. Today we are going to talk about something called wave equation. It's the equation which is supposed to describe the oscillation or vibration of just one string. So if you have a guitar around or a violin or any instrument which has strings, you can probably see that. So when you're playing one string, it starts to vibrate. It maybe wouldn't be easy to see that with just naked eye, but there's an experiment you can do. You can use a camera to kind of capture the vibration of the strings, right? I want to show that to you. I'm going to use, actually I tried to do that at home and use my own guitar to do that, but unfortunately the camera, the webcam is not good enough to kind of manage that. So I'm going to just show you a video online. So let me share screen with you. So if you look at the strings carefully, you would see how they vibrate, right? And today, that's what we want to do. We want to write down the equation for the vibration of these strings like that. And then we like to see what is the function which describes this vibration. Just by looking at the strings, you might be able to guess what is the function which describes the vibration. And so if you look how the strings would move, you might guess the function should be a trigonometric function, something like sine or cosine. That might remind you of the graph of sine or cosine. And we are going to see if that's the case or not. Great. Okay, so let's start. Let's start to write down the equations. Okay, so suppose we should decide about the kind of the framework of the question. So suppose we have a string like this, and just similar to string you have on a guitar, and both ends, suppose they are fixed, right? And then when you play the string, you kind of move with your finger, you would move the string to some other position. So for example, your finger would move the string in this position. Suppose you're holding it there and then you leave it, or you're playing it and it's going up and down. So it would start to vibrate, right? So the string probably would go up and then it would go back down. But actually, the way the string is going to look like might be even more complicated. It's not just going up and down just like an arc. You might see some more confusing things. Let me, if I can show that to you. Okay, take a look at this. So here we have
Another way to look at resonance is to look at what are called modes of vibration on a string. A mode is just a frequency at which a string, like the one shown here, wants to vibrate naturally in exactly the same way as a simple harmonic oscillator wants to vibrate naturally at some frequency. What we have here is a string that's anchored on one end. On the right-hand side, you can see it's tied onto a clamp that's clamped to the table. And on the other end, I've attached it to what used to be a perfectly good mid-range driver and now won't work very well ever again. We'll see in a minute. I'll zoom in on some of the details here to see how this thing is going to work. But the idea is that we're going to use the mid-range to inject energy into the string. We're going to move it at different frequencies and see what happens. See how the string behaves if we move it at a very specific and a well-chosen in advance frequency to see if we can force it into behaving as it normally would when it's ringing at one of its modes of vibration.
Guys, is the audio also understandable? Or the lag doesn't allow you to hear the video well? Okay, great.
So you can see here, this is a close-up of what I've done to that poor mid-range. I've glued a post, in fact it's just a wood screw, onto the dust cap of the mid-range, and I glued some small sticks on there to keep it upright because the string is pulling it sideways a little bit. What we're going to do is move that driver, the loudspeaker, up and down, and that's going to, of course, move the string up and down, as we'll see now. So here we can see what's happening. I'm driving the loudspeaker with an amplifier attached to an oscillator. The volume of the amplifier determines the amplitude, so how much the woofer is moving up and down, and the oscillator I then use to determine the frequency, which is how many times per second it moves up and down. And as you saw a minute ago, the other side of the spring is attached to a clamp. I can change the frequency. This is about 5 Hertz going up to, this is something like 10 Hertz, 9 Hertz or so. So 9 times per second going up and down. Or I could go the other way. I can go back down to 5 Hertz. That's 5 Hertz right there. Or I can go all the way down, for example, to 1 Hertz. So this is moving up and down and back up again 1 time per second. So this is the whole system again. I'm now driving it at something like 5 Hertz, 5 times per second, and I'm going to increase the frequency bit by bit. This is maybe 6, 7 Hertz, up to 8, 9 Hertz. And suddenly you'll see when we hit 11 Hertz, which I've already found out to be a magic number, what will happen is that the string will suddenly behave differently. This is 10 Hertz, and this is 11 Hertz right here. So you can see now, we'll freeze this. The string is in what's called its first mode of vibration. This is the frequency, 11 Hertz, for this particular string and this particular setup. This is the frequency it wants to resonate at, the lowest one, this 11 Hertz, so 11 times per second. What you can see is that even though we haven't changed the amplitude, the amount that the driver, the woofer, is moving up and down, the amount that the string is moving up and down in the middle has changed dramatically. And that's because it wants to ring at this frequency. Let's start the video again and see what happens if we increase the frequency again. So this is 11 Hertz. Let's move it up. This is going up to something like 15 or 16 Hertz, right? Let's see, right here. So we've changed now, we're moving faster, still at the same amplitude on the woofer. Now let's go to 22 Hertz and see what happens. At 22 Hertz, and remember our first mode of vibration was 11 Hertz. At 22 Hertz, you can see what we have here is the second mode of vibration. So this is the next frequency up that the string wants to vibrate at. 22 Hertz is 2 times 11 Hertz, so it's twice the frequency of the first mode of vibration. You can see again, I've frozen the video here so you can see what's going on. What's happening now is that the string naturally stops vibrating in the middle, but we still have 2 large excursions, 2 points where it's moving much more than the woofer is on either side of that point where it's stopped. But this happens naturally. I haven't done anything to the string to make this happen other than to put in the frequency where this mode wants to vibrate. So let's start the string moving again. I'll start the video moving again, and we can see what happens if we keep going up in frequency. So this is still 22 Hertz, and then we changed to something like 25, 26 Hertz, and we lose that resonance. Now let's go to 33 Hertz, which will be the third mode of vibration. Here we are. Again, I've stopped the video so that you can see what's going on here. It's basic.
Okay, great. We can stop this here. In your homework, I want you to go back. The homework for this week would be go after we learn this section about the wave equation. I want you to go back and watch this video and write down the equation for this string in this video. What is the boundary value condition? And then try to explain why we see this phenomena based on the equation we have. So that is the idea. I would put the link in the homework so you would be able to watch that again. Great. Let's start looking at the vibrating string mathematically. So again, just like a string on a guitar or any other string we have, what we are going to do is that we are going to assume we have a string with finite length, right? Let's say it starts from some point 0, x equals 0, and it goes up to some point x equals to a, right? And then just by some initial force, suppose this string starts to move, and suppose it's in some position when we look at the string. Suppose it's something like that, right? Now here we have the x-axis, and let's say we are looking at the string at some point x. I would denote this point x. Suppose I'm going to look at a point which is very close to the point x, just nearby, let's say x plus delta x. Suppose this is a point very, very close to the x, just let's say on its right side. Okay, so let's say at time t, as the time passes on, let's say at time t, I'm going to measure this distance, how much the string is above the x-axis. Let's say at time t, at point x, I'm going to show distance with u of x and t. So in other words, if we have also the y direction, this is going to be the u of x and t at the time t. So we have similar thing for this other point. If we are going to look at if we are going to measure this distance from the x-axis, we would get something else. If we look at it at the same time, we are going to get u of x plus delta x at time t, right? Great. So let's focus on this part. Suppose we have a magnifier right here, and we are just looking at that part there. Okay, so what we are going to see if we look from very, very, very closely, it would be something like this, where this is the point x, and this other one is the point x plus delta x, and at some time t, we are looking at this small, very small piece of the string. Okay. So in order to study how this string moves, we should study what are the forces which are exerted on this piece of a string. So I'm going to assume that at some point, I've kind of I used some force to move this string, like just when you play a guitar, right? And I'm assuming now it's moving. So at time t equals 0, I'm assuming the string is already moving, okay? So in another sense, I would play the guitar and then I would start my clock. I would let the clock count. So at t equals 0, when I'm looking at the string, there is no force, for example, by my hand or any other source, any other outside source anymore. So when we start, the string is in some initial position and it's already moving, right? So we should study the forces here. And what I'm telling you is that there is no force from my hand or any other source. The only force which we have here is, of course, the gravity. So the forces in play are, one is the gravity, of course. And the other one is just what we call the string tension, the tension between the particles of the string itself, right? When we look at the string, each part of the string kind of pulls the other part. That's how they kind of stay connected. There is some tension between them. Okay, so the string tension. So I'm assuming these two are the only forces here. So I'm assuming there is no resistance in string. It's completely flexible. We are assuming all these things because, well, mathematically, that makes things a lot easier. Okay, so let's focus on this graph we have here. So it was like this. We had some point x, and we have some point x plus delta x. Let's show the tension in the string bar at the point X at time T. Let's show that with, so the tension at the point X at time T, let's show that with T of X and T. Great, I'm going to denote it with T of X and T. Now that is, T of X and T is, the point is that it's a vector. It's not a number. It shows also the direction of the tension. So for example, if I look at this point, the tension would be something in direction of the string. So the tension would be something tangent to the direction of the string at that point. So here, this vector would be T of X and T. However, we can kind of guess what the direction of this tension would be, because if the string, for example, is in a position like this, you can assume the string wants to come down. So if you look at this point, probably the string is pulling back this segment. We are looking back downwards. So it's not, for example, in that direction. It's in the other direction, right? Well, anyway, I mean, in other situations, the direction might be different. I don't care about that now. And at the other point, the tension would be something, again, tangent to the direction of the string. It would be T of X plus delta X at time T, right? This would be the tension at these 2 points. Now, the other thing we have is just the gravity, which is downwards, right? And we showed, if assuming the mass of this string is m, the gravity would be mg, right? And it's downwards. Okay. So if I look at this horizontal direction and then look at this vertical direction, if I call this angle here, the angle you see here between this graph and the horizontal direction, if I call that alpha, I know that this T would have one component in the horizontal direction. That component would be T of X and T cosine alpha. And it would have one component in the other direction. That other component would be T of X and T sine alpha, right? Same thing holds for the other one. So if at the other end of this segment I'm looking, if I look at the horizontal and vertical directions, if I call this angle beta, I would have one component of T at that point in horizontal direction, which is T of X plus delta xt cosine beta. And then another direction, which is T of X plus delta X and T sine beta, right? Now, this angle is different at different points, right? At some point, we showed that with alpha, in the other point, we showed that with beta. Let's choose a kind of notation for this angle. So if I'm looking at this string here, which might look like this, or even might be more complicated. So let's say the string is something like this, and this is my x-axis. At each point x, at time t, I can look at the angle it makes with the horizontal direction. I'm going to show that with phi of x and t. So this is phi of x and t. In the example we have on the right-hand side, on the left-hand side, phi of x and t is equal to alpha, and phi of x plus delta x and t is equal to beta, right? That's the notation we are fixing to denote this thing. Now, when this string is moving, for example, when you're looking at the string of a guitar, in some sense, the movement of the string is just in up and down direction, right? The string would go up and down. It doesn't move to right and left, right? There is no move in the horizontal direction. It only moves upwards and downwards. In another sense, there is no acceleration in direction of right and left. So using Newton's second law, we know that the force, the total force in the vertical direction, sorry, in the horizontal direction should be 0. What is the total force in the horizontal direction? So there are two components. As you can see, in horizontal direction, one is this one, T of x and t cosine alpha. And then there is another one, which is here, T of x plus delta xt cosine of beta, right? So one is here, one is here. They're in different directions, right? Their algebraic sum with plus minus should be equal to 0, because that would be the total force, and that should be 0. So I'm going to write that down here, just next to things we have. So if I take the right-hand side as the positive direction of the x-axis, we have minus T of x and t cosine of alpha, but I'm showing alpha with phi of x and t. That's the angle at the point x at the time t, plus T of x plus delta x t sine of beta, which now we show that with phi of x plus delta x and t. This sum should be equal to 0. Okay, is that clear to everyone? Is everyone following? Why is that the case? So this is the total force in the horizontal direction, and because the string is not moving in horizontal direction, it's not going left and right, this should be 0. Great. So I take one term to the other side. So we have T of x and t cosine of phi of x and t is equal to T of x plus delta xt sine of phi of x plus delta x t. Right, great. So if they are equal, to each other, if I'm looking at my string, let's say string is some arbitrary position like that. If I look at it at the point x, and if I look at it at the point x plus delta x, this tells me that t at the point x times cosine of phi at the point x is equal to t at the point x plus delta x times cosine of phi at the point x plus delta x. Now, this is correct for every x. So I can take this one as x prime. Let's say this is x1 and this is x1. Let's call this thing as x2. Therefore, t at this point x2 times cosine of phi at this point x2 should be equal to the same thing for another delta x, assuming delta x is not very large. There's a reason for this assumption, but anyway, assuming delta x is not very large, you can go one step further, and you see it would be equal to T of x2 plus delta x t cosine of phi of x2 plus delta xt. With some mild assumption, it shows you that doesn't matter which point, which x you choose, t at that point times cosine of phi at that point is something constant. All of these things are equal to each other. So let's call that number t. So the conclusion is that at any point x, T of x and t cosine of phi of x plus delta x and t is equal to something constant. Actually, sorry, phi of cosine of x and t. Actually, here in our assumption, in the way we describe this problem, doesn't matter even if delta x is large or small. So in other words, for any other point y, we can say y is equal to x plus delta x. So this would be equal to T of y t times cosine of phi of y and t, right? So it's independent of the point x. So this is independent of x. It's independent of this variable here. Doesn't matter what it is. This product is always something constant, right? Under some assumption, it's even doesn't depend on the other variable t, the time t. So if you're assuming that our string, if we assume the length of the string does not change, right? So for example, if you have a spring, if you pull it or push it, its length would change. But here, if we assume the length of this string does not change as it goes up and down, it's also in this product is also independent, would be independent of t. So it's independent of the first variable, also independent of the second variable, as long as they are equal, right? The first variable here is equal to this one, and the t here is equal to this one. So in other words, if I change this t to another s, we still would have this equality. So it's a constant. Let's call that constant. Let's denote that constant with capital T. Great. Is there any question up to here? If there is any question, you can unmute yourself and ask. Okay. So do not hesitate to interrupt me if there is something non-trivial or confusing. So now that we know this thing is constant, let's keep that as a part of information. Let's denote that with star. The fact that t cosine of phi at any point x and t is something constant. Let's denote that with star. Now let's look at, we only looked at the horizontal direction. Now let's look at the vertical directions. So this is the x direction. And we are looking at some small segment of our string. This is the point x. This is a very nearby point, x plus delta x. And then if tension at this point, for example, is downward, tension at this point would be upward. So the directions of the vertical component of t at these 2 points is different. If I decompose this vector on the right-hand side into 2 components, I would get the red one and the blue one. One of them is upward, one of them goes to right. At the other point, one of them is downward, one of them goes to left. Great. So this blue vector here, its size is equal to minus t of x and t sine of phi of x and t, considering this negative because it goes to left, plus this other one here is equal to t of x plus delta x and t sine of phi of x plus delta x and t. Okay, that's the total force coming from string tension in vertical direction. But there is one more thing. There is gravity. Gravity is downward. So we have mg, but the point is that gravity is always going down. So we consider gravity with negative sign. So these things we have minus mg. This is the total force in the vertical direction. Now, by Newton's second law, if you remember, total force is equal to, in both vertical and horizontal direction, or in every direction, is equal to ma, where a is the acceleration in that direction. So this thing is equal to ma, which a shows the acceleration in the vertical direction. Is this equation clear? Any question here? So this is Newton's second law. Now, let's call this one star star. star, star. Now the point is that we know what is acceleration here. So if this is our string, if this is, for example, acceleration downwards here at this point, if we are showing the position of the string at point x and t with u of x and t, acceleration can be stated as derivative. Actually, acceleration is the second derivative. So remember, velocity is the first derivative with respect to time. Acceleration is the second derivative. So a is the second derivative of u with respect to time. Combine this thing with the equation we had here. We should replace the acceleration a with the second derivative of u with respect to time. What do we get? Let's write that down. So what we had earlier was minus t of x and t cosine of, sine of, we were in the vertical direction, sine of phi of x and t plus t of x plus delta x and t sine of phi of x plus delta x and t minus mg is equal to ma, which here would be the second derivative of u with respect to t xt. Okay, so this is our equation in the vertical direction, right? So this is the vertical equation. Let's call this one vertical equation. What was the horizontal equation? The horizontal equation was that t of x and t times cosine of phi of x and t is equal to a constant, and we call that constant t. So the same, it's equal to the same thing at x plus delta x equals to, we said it's a constant. We showed that with star. So we have these two equations. These two equations should describe our string completely. Take a look at them for a second. Is there anything confusing in these equations? Is it clear to everyone how we got these equations? Okay, great. So let's use this equation to write down t in terms of cosine. So here, if I look at the first part, t times cosine of phi is equal to t, it shows me that t at the point x and t is equal to this constant t over cosine of phi at the point x and t. I can look at this other equation, t at x plus delta x and t times cosine of phi at x plus delta x and t is equal to constant t. Therefore, again, t of x plus delta x and t is equal to the constant t over cosine of phi x plus delta x and t. Can anyone tell me why I'm allowed to divide by cosine? Why I'm allowed to divide by cosine? Well, we are not dividing, you are certainly right, but we are not dividing by t, we are dividing by cosine, right? So it means cosine should be non-zero. So yes, so we are allowed to divide, so we have t of x and t times cosine of phi at the point x and t, it equals to constant t. We divide both sides by cosine, so we get t at the point x and t is equal to this constant t over cosine of phi at the point x and t. So we can do this thing with this assumption that this is non-zero. Why this thing is non-zero? So suppose this is zero. Let's see if it's possible for cosine to be zero. What does it mean for cosine of phi at some point x time t to be zero? If it's zero, it means phi is equal to plus or minus pi over 2, right? But that doesn't seem to be realistic for our string, because if the angle is pi, it means the string is like this. So the string is just going up, right? You don't expect to see that for a vibrating string. You don't see this the string completely becoming vertical, right? As long as it's intact and it's not broken. So you wouldn't expect to the string to become like that. So so it makes sense to assume phi is not equal to plus or minus pi over 2. Therefore, cosine is non-zero. Therefore, I can divide the equation by cosine of phi. Great. Now, let's go back and look at the equation we had here. No, not this one. This vertical equation. So I can replace this t here by what I have here, because they're equal, and I can replace this t here by what I have here. So that's what I'm going to do. I'm going to replace t of x and t by this constant t over cosine of phi. Same thing for the other term. So if we do that, if we replace t by that, we would get we had minus t of x and t. We are replacing that by the constant t over cosine of phi at x and t. This is what we had before, and we were denoting it by t of x and t. We replaced it by this new thing. Times, well, what was the rest of the equation? Sine of phi at x and t, plus, then we had t of x plus delta x and t. I'm going to replace that by t over cosine of phi at x plus delta xt. So this thing is, we replace t at the point x plus delta x and t with this new thing, times sine of phi at x plus delta xt, right? Minus mg equals ma, where a is the second derivative. Now, sine over cosine is tangent, right? So what we are going to get is that minus t tangent of phi at x and t plus t tangent of phi at x plus delta x and t minus, well, it's equal to m. I take mg to the other side. It's equal to mg plus the second derivative of u with respect to time. Okay, right? Great. So here we have m, and m is the mass, and we can think about the string having kind of uniform mass. So if we look at some, if we show the mass with rho, I'm kind of think about it as kind of linear mass. So I would linear density. So I would define rho to be I would define rho in this way. So look at the string and consider some length, say delta x. Okay, and I can look at the mass in this length, the mass of the string in that segment, just above delta x. So the mass of this red segment. Okay, let's show that with m. If I divide m by delta x, I would get this kind of linear or kind of one-dimensional density. Okay, so I can, in other words, In other words, m is equal to rho delta x. Okay, so I can replace this m here by rho delta x, which rho is a kind of density. I'm not considering the area of the string. I'm just thinking about it as something one-dimensional. Great. Okay. Okay, so let's rewrite this equation. Let's go to the next page. Okay, I would write the equation again here. Minus t tangent of phi at the point x and t plus t tangent of phi at x plus delta x, and t is equal to delta x rho times g plus the second derivative of u with respect to time. Okay, now let's divide everything by delta x. So what we are going to get is t tangent of phi at x plus delta x, and t minus t tangent of phi at x and t over delta x is equal to rho times g plus second derivative of u with respect to t, right? Now, let's divide both sides by t. So if I divide both sides, we would have a t on the right-hand side, then we would cancel the t we have in numerator. Now, on the other hand, if phi at each point x at time t, if this phi at x and t tells us what is this angle here with the horizontal direction, its tangent would be the slope of this line, right? So if phi is equal to the angle with the horizontal direction, tangent of that is equal to the slope of the tangent line. Right, we have a curve. This string is like a curve. We have, at each point x, we can look at the tangent line. If this angle is alpha, tangent of phi, which is tangent of alpha, would be the slope of this tangent line. But the slope of the tangent line we know is equal to the derivative of the function. So if this function is u, tangent of phi would be equal to the derivative of u with respect to x. Okay, is that clear for everyone? Oh, someone said, are we assuming t is non-zero? Yes. Oh, it's the answer to the previous part. Yeah, also here I'm dividing by t, so I'm also assuming t is non-zero. There's tension keeping this string together. So tangent of phi is equal to derivative of u with respect to x. Now going back to this equation, it means tangent of phi at this point x plus delta x is equal to derivative of u with respect to x at the point x plus delta x and t. And this other term is equal to derivative of u with respect to x at the point x and t. Let's rewrite this equation. Let's just write down what I wrote there one more time. So we have derivative of u with respect to x at the point x plus delta x and t minus derivative of u with respect to x at the point x and t over delta x. This is equal to rho over t times the second derivative of u with respect to t plus g. But what is this thing? Take a look at this thing carefully. We kind of know what is this. Forget about how this derivative of u with respect to x might look like. That might confuse you a little bit. Let's call the whole thing here g. We have g at the point x plus delta x minus g at the point x over delta x. So, so in other words, if I change the notation here, we would have g at the point x plus delta x minus g of x over delta x. What is this? This is just derivative of g with respect to x by definition of derivative, right? But here g itself is derivative of u with respect to x. So this thing here is derivative with respect to x of derivative of u with respect to x. So in other words, it's just the second derivative of u with respect to x. Okay. Now we have second derivative of u with respect to x is equal to this right-hand side here. Let's rewrite that. The second derivative of u with respect to x is equal to rho over t times second derivative of u with respect to t plus this g, the constant of gravity, the gravitational acceleration. Okay, great. So what we can do here. So the point here is that if usually it's common, I think, for reasons from physics, which I'm not very much aware of them, not very familiar with them. Usually they show rho over t with c squared. It's just a constant. So using this notation, we have the second derivative of u with respect to x is equal to c squared, second derivative of u with respect to t, plus c squared g. Now, assuming that gravity has not much effect on our theory, for example, look, you're looking at the string of guitar, assuming that gravity doesn't really do much vibration, the gravity doesn't affect much vibration, is not a bad assumption. Of course, when you're playing guitar, gravity affects strings, but you think it shouldn't be much. Well, it holds the air around, that allows the sound to travel. But if you just, for the sake of one string vibrating, that doesn't have much effect. So we might ignore this part which comes from the gravity. If we do that, what we are going to get is the second derivative of u with respect to x is equal to a constant, doesn't matter what this constant is, times second derivative of u with respect to time. This is what we usually call the wave equation. Okay. So this is the second interesting PDE we have in this course. There is usually a interval which this thing is defined. Let's say x is bounded between 0 and a, and t is positive, just like the boundary conditions and initial conditions we had for heat equations. There are such things here too. So writing down the equation completely, we have the wave equation, which is this thing. We have the boundary value conditions, which tells us that what's going on at this point and what's going on at this point. So here, for example, I'm assuming that u at the point 0 at this point at any time t is fixed and it's 0. So it's like your guitar probably. So this is the endpoints are kind of fixed, right? When you play the string, the endpoints do not move. Same thing goes for the other end. Right, and there is some initial condition. So this is, for example, suppose this thing is at the time t equals 0. You start at some point. So at time 0, at every point X, this thing is given. But there is a difference here with the previous equation we studied. In the previous equation, this initial condition was enough. But here it's not the case. You know, when some string is moving, telling you that, for example, at t equals 0, the string looks like this is not enough. Because maybe the string like this, but let me draw something simpler. So let's say the string at t is equal to 0 is like this. You don't know that the string is moving upwards, it's going up, and at some t equals 0, you saw this string and it looks like this, or it's going, or on the other way, or conversely, it's going back down. You don't know that. So you also want to know which direction it's moving towards, how fast it's moving. In other words, you need to know what is the derivative of u with respect to t at time 0. So we are assuming that these two things are given. So the initial condition is a slightly different with the equation. Great. So the whole thing is our package of the wave equation. Is there any question about the things we discussed up to this point? Great. If it's clear, we can stop here. So this was section 3.1. If you are following the book, in the next section, we are going to try to solve this problem, and we would see the techniques we learned before, they really work pretty well here too. We would try to solve this one and we would be successful actually. So let's have a break. Let's have 10 minutes break.